I had 25 years, and that doesn't include study, for close to 30 years in resources, oil, gas, metals, and other resources. The single largest energy usage globally is for heating and cooling. That's over 40% of our energy use goes into that alone. And at the moment, there's nearly zero renewable penetration into that. Alone today, geothermal can solve 40% of the world's energy needs. With technology advancements in the next 5 years, that can double. And with technology advancements in the next 15 to 20 years, we can potentially even double that again. There is no other technology that's available today that can do as much as quickly. Now, within Causeway, we're looking at both. So what we want to do is decarbonize that 20% that we can decarbonize today while we're developing the technologies for tomorrow, and with an eye on the technologies for the next decade. Geothermal actually is just a source of energy. So how we use that energy is limitless, and how we use that energy is really just confined by our own imaginations. I'm fascinated by closed loop technologies because closed loop technologies allow us to deploy locally. They allow us to deploy anywhere. And really, they're a techno-economic issue, not purely a technology issue. They're really about how do we do this efficiently and effectively so we make it affordable. As we go down that learning curve, which is really starting for closed loop systems, what we can see is a future where geothermal plays a massive role in delivering base load energy for all of the critical energy requirements that we need, be they heat, cooling, or electricity. So we don't really see boundaries in terms of what it can do. What we see is opportunity. Not only do you bring affordability, you bring sustainability, you bring security of energy supply, and there's nothing else that can beat that anywhere in the world today.
Good morning or afternoon or evening, wherever you may be in the world. My name is Eli Dourado, and it's my pleasure to moderate today's panel on engineered working fluids. Unlike many of you, I don't come to the geothermal world by way of the oil and gas industry. I'm a policy researcher at Utah State University's Center for Growth and Opportunity, where I focus on removing the barriers to transformative technologies like advanced geothermal that will lead to a radically more prosperous world. When I learned that there are orders of magnitude more energy in the form of heat in Earth's crust than in all the fissionable material and fossil fuels on the planet, I realized I had to be part of the solution to help unlock this enormous energy resource. We have an experienced, distinguished, and excellent panel today to discuss how to capture more of the 15,000 yotta-joules that are in Earth's crust. We'll bring up the panelists up on stage now, and I'll ask each of them to explain who they are and what they're working on with regard to engineered working fluids. So Michael, you first. Welcome. Can you please just tell us who you are and what you're working on?
Sure. Good morning, or good afternoon, good evening, everybody. My name is Michael Hill. I represent Sage Geosystems. I'm also new to the geothermal space and very excited about being involved in the energy transition businesses. But unlike Eli, I did actually grow up in the oil and gas industry. So straight out of college, my first job was on an oil refinery, which really gave me a good grounding in different processes and different systems, both from the maintenance and capital project side. I then took a good time in private practice as a consulting engineer, principally designing process equipment, so heat exchangers, pressure vessels, distillation equipment, reactors, and the like. Right now, I'm excited to be working with Sage. We're moving rapidly towards designing and building our first plant with the view to developing a geothermal anywhere solution. So I do interact a lot with the subsurface stuff, but principally I'm involved in the surface equipment, the power plant design and development.
Great, thank you. Alvaro, you next. Who are you and why are you on this panel?
Hi, everyone. My name is Alvaro Amaya. I am the Chief Modeling Engineer at GreenFire Energy. I have worked as a professor in geothermal and thermodynamic topics in the University of El Salvador and as a researcher in Japan. I held a Ph.D. in geothermal modeling from Tohoku University and my master on hydrogeology and my bachelor degree on chemical engineering. And I also would like to introduce GreenFire Energy. GreenFire Energy is a closed-loop geothermal company, and in GreenFire Energy, Our immediate commercial focus is in retrofitting unproductive existing geothermal wells and expanding within existing geothermal resources with new purpose green loop wells to make them productive, where conventional geothermal use won't work or the resource have water or pressure depletion. Additionally, there are in our company 3 leader investors that recently have invest in our company. They are Baker Hughes, Valorec, and HMP. So as a group, we think that we can work in different solutions for power, direct, and also industrial application, offering geothermal, oil and gas, and district heating designs for different purposes. Thank you.
Great, thank you. Jordan, can you tell us who you are and what you're working on?
Yeah, great. My name is Jordan Nielson. I work at Southwest Research Institute, which is a third-party, not-for-profit engineering firm. And I came into the geothermal from the power systems and turbo machinery side, actually. So about 7 years ago, our company worked with the Department of Energy for a CSP, concentrated solar power application, and found that CO2 could give pretty high efficiencies. And so we've been working on filling technology gaps for CO2 power cycles. And then from there, we funded an internal research project specifically looking at a thermosiphon or natural convection waste heat recovery application, and found that one of the best applications that could actually be feasible for was geothermal. And then from there, we've kind of dug out and looked a little bit more outside of just thermosiphon, and also doing turbo machinery design for low enthalpy CO2 geothermal applications.
Great, thank you. Alberto, please introduce yourself. Tell us why you're here.
Hi, everyone. I'm Alberto Mian. I'm an energy engineer. I am the CEO of ExerGo. ExerGo is a Swiss startup that is commercializing an innovative district heating and cooling system, which uses CO2 instead of water as a working fluid. So we have been developing this concept at the Polytechnic School of Lausanne in Switzerland since 2008. We have our demonstration plant running. He has been put in operation last month. And we have a technology that is really easily pluggable with shallow geothermal application for heating and cooling. And it can also provide an effective solution for geothermal power plant cooling. So
great, thank you.
Yeah.
So I'd like to make this panel as much as possible a discussion, not just me peppering individual people with questions. So let's try to do that. But I'll kick us off, and I think we should start at the very beginning, which is kind of like, what's wrong with water? Like, why should we have engineered working fluids, and why are they desirable? And I want this to be a discussion, like I said, but maybe Jordan, you could kick us off.
Yeah, sure thing. So like I said, we kind of started from a slightly biased opinion, kind of coming from concentrated solar power. And the reason we looked at CO2 for that application specifically was because it gave higher efficiencies than water. So that's at higher temperatures. But for waste heat recovery applications, there's lots of benefits of the fluid itself. Where its density is at, where its critical pressure is at, and how much density it swings near ambient conditions that make it useful, especially when you're looking at lower heats.
So anybody else have thoughts on that? Or like, how would you explain to like your mom, like why should we use an engineered working fluid rather than just water?
If I can answer, so I would say an engineered working fluid, and in my case, CO2, CO2-based working fluid. The basic idea behind that is it's all about energy density. So if you take a water steam cycle, one of the issues in this kind of systems is that the vapor has a very low density. So when you leave your turbine cycle, at the outlet of your steam turbine, the fluid is has a very poor density, which brings equipment to be very large. One of the advantages of having an engineered working fluid is that, especially CO2 in our case, is the composite. So we have a fluid that has in a vapor state a density which is up to 150 kg per cubic meter, which means that you have a lot of, and then you can profit from the phase change of the fluid, which gives you basically a very dense fluid that has a dense energy density, which brings, so you are working with the efficiency of the cycle and the temperatures you can get, but also with the composite of the equipment that will allow you to produce power. And this, I think, is the beauty of developing working fluids for power plants.
Great, thank you. Any other thoughts on that before I?
Yeah, I think maybe just to highlight the fact that with geothermal, we can get very hot rock, obviously, if we go deep enough, but the typical levels where we're looking at commercially viable, we're only dealing with around 120 to 150, maybe 200 centigrade, so 200 to 250 Fahrenheit. So that kind of cuts water out for going through phase changes that we need to get power extracted from it.
Mm-hmm. I also would like to add that there are three main categories of characteristics that makes a particular fluid a good match. Like, for example, environmental characteristics, performance characteristics, or thermodynamic characteristics. Those three characteristics are very valuable for projects to make them success. So, as for example, for environmental characteristics, we need to choose working fluid that could have low emissions. For example, it can produce product with small footprint areas. And for performance characteristics, we need to choose working fluid that are, for example, as Michael and Alberto mentioned, high compressive, inexpensive, or relative inert and high efficiency characteristics. And also the thermodynamic characteristics are very important for choosing the working fluid.
Great. Can we talk also about thermosiphoning and sort of the benefits there? Alvaro, do you have thoughts on that?
Sure. Yeah. The benefits of thermosiphon processes is that it controls and interacts with the four ways of energy. They are the thermal energy, the kinetic energy, gravitational energy, and pressure volume energy. So, for example, in a wellbore, this means that we can control by designing the correct geometry and designing the correct conditions and optimal performance of the system. This means optimizing the power production, the net power production, and minimizing the parasitic pumping power. So in our experience in GreenFire Energy, we had a demonstration project at COSO in between 2018 and 2020, where we proved the efficiency of downward heat exchanger in a specific location in COSO. But also we use water and supercritical CO2 as working fluid, and then we corroborate the advantage of thermosiphon process. We have published those results and papers in our website, but in basic, the results show that a downward heat exchanger can extract efficiently the heat from geothermal resources, and also by using the thermosiphon processes of working fluids, we can optimize the net power production.
Anyone else have thoughts on thermosiphoning?
Yeah, so that's kind of how we came into the geothermal world originally. And again, maybe just to back up a little bit, a thermosiphon, if you think of siphoning your car, is basically creating flow with density and height change. We looked at how you could do that in an actual cycle. And what that means is having a dense fluid coming from a high location, elevated, then getting heated at a low location, so its density reduces, and so it's able to flow back up. And so you're able to create a natural flow with a thermal siphon without a pump, as Alvaro stated, and pump or compressor. And that really helps with parasitic loads for a power cycle. A compressor is also the hardest component to get high efficiencies and is also a high maintenance component. So it makes it easier to run. And compressor / pumps, especially for high speed turbo machinery, they kind of don't like to go between phases or go into the dome. That can be really damaging to compressors, especially. And the thermal siphon itself, we tested at our facility, which was small, but we were able to go through the phase change and go into 2-phase and maintain the thermal siphon. And so it also appears to be more robust. So there's lots of elements to that. And then, like I said, the thermal siphon is driven by the fluid properties itself. And so CO2 works out really well because it has really big shifts in density, especially near ambient conditions. So you don't need like a chiller or something per se to cool it off to its dense phase. And so, yeah, there's lots of benefits. Couple challenges as well, but lots of benefits that make it exciting.
I think one other benefit to keep in mind is that,
do we know like how much like parasitic load, like in terms of like percent and efficiency, do you guys have thoughts on that?
So generally for a Brayton cycle at these lower temperatures, your pumping power is about half of your gross power output. So basically half of the power that you're producing is going back to running that pump itself.
Yeah, it's pretty significant. Michael, you were going to say something.
Yeah, sorry to jump in there. I was just going to point out as well that one of the other attractions of the thermosiphon is that you're going to a non-binary system, because effectively you're taking the working fluid and exchanging that with a downhole heat directly. So you're saving on a bunch of equipment there as well.
Great. And any downsides of using this process?
Yeah, maybe in our case, we have used and tested thermosiphons to distribute low temperature energy. What we have seen is that we should also distinguish between processes that are running almost steady state and processes that have multiple startups. We have seen that in a thermosiphon of even more than where a denivelation of more than 100 meters with multiple startups, that one could have bubbling in the liquid lines that could really prevent from the thermosiphon to starting. We are talking about application where we exchange heat between I would say 5 and 25 degrees C. So we are really in the subcritical region of the CO2 as a fluid. So in some cases, we have seen that really the need to start the process, the need of a pump to start the thermosiphon can really speed up the starting phase of the thermal exchange. Another thing that we have seen is that there is, it's also about the thermal sources we have. So with stable thermal sources, the flow going through the thermosiphon would be basically constant. But in some applications, if we are able to control the flow, so for example, to a shallow geothermal with a water circuit, and where we can play with the amounts that are extracted or injected into the geothermal site with a variable flow pump. In that case, we have seen that the delta T, so the pinch point, the delta T at the interaction at the heat exchanger between water and CO2, it's much higher than if we have a pump and basically an electronic expansion valve that can really control the delta T between the two fluids. So this is our experience with the thermosiphon. But definitely it's a very attractive solution for steady state, I would say for installations where we have constant heat loads, where we start up the process and we are not going to disturb the thermosiphon. And once the thermosiphon is created, it just keeps running.
Great. Should we shift gears a little bit and talk about turbo machinery? So I've heard people say many times that with other working fluids, including CO2, the turbo machinery can be smaller. But can you guys give us an idea of like how big? Like why does that matter? Like how big is steam turbo machinery? How much smaller is CO2 turbo machinery? Any thoughts on that?
So I think Alvaro mentioned that earlier, but that's one of the things we've now built quite a few turbo machines for CO2. But generally, we're talking about a CO2 turbo machine being something that can fit on your desk, and a water turbine is something that's probably couldn't even fit on a flatbed truck to truck around town. So it's on the order of 10 times larger usually for an equivalent power rating.
Yeah.
And I think that mostly helps in theory to reduce cost of your what's needed to start or get your power plant up and running.
Yeah, the size of the turbo machinery is related to the efficiency of the global process. And also this topic is related to another topic that is, for example, decentralization of power production. That is other alternative that can produce important savings in a project. So for example, the production on field, so is another important topic. Instead of having a centralized unit that produce for delivering power. So all these topics, the size also is related always with money, because it will reduce the footprint area and also would reduce the cost of operation and maintenance at the end.
Yeah, I think for us at Sage, it's really important to have the small size equipment to suit the modular approach that we're taking, so we can literally pick up this kit and move it onto a site anywhere and relocate it if we need to. So portability and modularity is really important, and the reduced size is extremely helpful in that regard.
And are these CO2 cycle turbines, are they available off the shelf? Are you making your own? How are your projects approaching that question?
So we're looking at two approaches. One is to source industry available equipment, especially for these earlier projects, while we then work on developing a more customized design. And we're working closely with Nelson and his team at SWRI, Southwest Research Institute, on that specifically. And one of the approaches we can take with that is to build in flexibility in terms of changing the aero side, which allows us to try out and implement different mixes and designs of the working fluid.
Yes, similarly in GreenFire Energy, we also can match any surface condition or any surface machinery. Also the CO2 expander, as well as other working fluid expanders, organic Rankine cycles, for example. So in GreenFire Energy, we see a project as a optimization process. So the working fluid selection is what is part of this optimization process, but also there are other elements or variables that we consider in order to make a project profitable and sustainable.
I'll also add to both of what they said. So at SWRI, like I said, we've built quite a few sCO2 turbo machines, but they've all been one-off prototype, which is what we're good at. We're not good at mass developing, but our industry partners have taken those designs and are looking to either mass produce those themselves or work with turbo machine industry partners to mass produce those. So currently not too many sCO2 turbo machines off the shelf is what I'm saying.
Yes, at ExerGo, we are mainly looking at also supercritical compressors, because we have a heating and cooling system that can provide this cooling energy services, but also heating energy services. And in our case, we are quite lucky because we can find supercritical CO2 compressors from the oil and gas industry, and these machines are suitable to be integrated in supercritical CO2 heat pumps. So where we basically reverse the cycle. We do not have a power cycle, but we are using electricity to provide high temperature heating energy services.
Great. I'd like to ask a little bit about like fluid optimization. Is it so? My understanding is it's site specific, right? You optimize the fluid based on the specific site. So how does that work, and what are you looking at in those cases?
So in our cases, was it for me? Sorry, I didn't understand.
It's for anybody. Yeah.
Okay. I let maybe Jordan or Michael have start to answer.
No, yeah, in our case, we're looking at different working fluids and trying to work out not the perfect one, but certainly a working fluid that will suit the typical conditions that we are probably going to be looking at installing plants at. So it's not plant specific, but it's more general application specific. So we're looking at, I think, as I mentioned earlier, a source temperature range of from 120 degrees centigrade up to around 200. So that's one starting point. And then the other is at the cooling end, where we need to cool down the fluid for repressurization. And those pretty much govern the start and finish points. And then we need a match a cycle in between that to get the best thermal efficiency out of the fluid. In other words, recover as much as we can of the heat and convert that into electrical power at the end.
Yeah, I'll also add to that a little bit. I think that might be kind of like the gold thing that's a little bit further down, is to actually optimize for site-specific conditions. But I guess the reason for doing that, I think using pure CO2 as an example, to understand why you would want to optimize your working fluid. Pure CO2, its critical point is at about 31 degrees C, somewhere in the high 80s F. And so if you have a 70-degree day outside and you're cooling with dry coolers, it's pretty easy to get to a very dense phase for a thermosiphon with CO2. If you're in Texas and it's the end of July and it's been 100 days for 30 days in a row, it's much harder to keep high efficiencies with CO2 because now you're at a much higher, you're a much less dense. And so the ability to move that critical point higher for hotter applications or areas would benefit your efficiency. It would also reduce your cooling parasitic load, like Michael was saying, because you don't have to have as big of a, or you get a much bigger DT to where you want to get. And so I think there are more optimal fluids than just using pure CO2 based on ambient conditions and downhole conditions. How we get there and what those look like, I think, is still kind of in the early stages of research.
I also would like to add that for working fluid selection, we need to emphasize, as Jordan mentioned, the potential of the resource, because in geothermal systems or in geothermal power production, we need to first analyze what is the potential of the system. So if, for example, if the system is an impermeable system, or if it is a steam dominant system or two-phase system, oil and gas, reservoir. So we need to estimate the potential of the resource, and then we need to design the system with, for example, different configurations like coaxial or U-shaped loops. In our case, we need to face also the selection of insulation materials. We need to design for different work flow rates, and working fluid is also need to be adapted to the geometry of the well. If it is a retrofit well, for example, or if it is a new purpose drill well, we can optimize the geometry, the diameters of the system in order to minimize the parasitic pumping power, and also the inlet and inlet condition of temperature and pressure are also important in all this optimization process, I will say.
Great. Well, we are just blowing up with audience questions, so maybe we could shift to some of those. So first question from the audience is, what are the risks of crystallization, solid deposition of carbonaceous material in the hull? What about corrosivity? So you guys have thoughts on that? Our in GreenFire Energy, we have different solutions for geothermal industry. One of our claims is that we can control downbore conditions by controlling the flow rate of the working fluid that we're injecting in the coaxial or U-loop system. So by injecting the correct amount of working fluid to extract the potential of the, for example, the feed zone or the potential of the system, so we can control the saturation or saturation condition if it is, for example, a two-phase or a steam dominant system. By controlling these conditions in geothermal system, we can avoid be in the range of temperature that are close to the saturation index of certain minerals, or we can avoid certain conditions that are more favorable to high pH, for example. So by controlling temperature and pressure downbore, we have a lot of advantage if we compare with conventional geothermal systems. So the closed loop system can be used for this purpose, for corrosion and scaling control. Any other thoughts on that, or we can move on to the next question?
So I'll add a little bit. I think it's a valid, definitely valid concern, especially using CO2. And I think lots of times we're kind of assuming these are closed loop systems, but that's not the case for everyone. And CO2 definitely becomes acidic when it's mixed with water, for example. So obviously for me that has a lot more experience top hole, not down hole, there's things with material selection on the turbine that you can do to overcome acidity. But it is a valid concern, and I think that one that needs further research, and one that we're doing with our materials group, looking at CO2 corrosivity.
Yeah, I think some of the systems we're looking at will involve using water or brine as the heat recovery fluid downhole, and that will also have its own challenges. But I don't think they are insurmountable. It's just a case of picking right materials to suit the fluids that we're going to be moving.
So another question from the audience is are we talking about replacement of ORCs with direct CO2 turbines? And you know, what are the efficiencies of CO2 turbines compared with ORCs? You guys have thoughts?
Yes, this is something we're trying to answer, I think internally, with a much better answer than I can probably give today. So I think there's always going to be a place for ORCs. I don't think what we're proposing completely gets rid of them. I definitely think they compete. There's advantages and disadvantages to both, and I'll fully admit that I'm biased based on coming from CO2, but even CO2 as a binary cycle, not the thermosiphon, you get some advantages because you're doing the hot heat exchange not through the dome, you're doing it in supercritical, so you can get much tighter pinches on your hot heat exchange. And And although this sounds kind of counterintuitive, what that means is even though the efficiencies for sCO2 cycles and ORC cycles are actually pretty similar at these temperatures, it might be possible to extract more heat with the sCO2 cycle because you don't have that pinch problem by going through the dome. And so your net power looks like it will go up. And then also, again, the density reducing footprint and upfront cost also seem to be beneficial for sCO2 versus ORC. But I think in certain applications, the thermal siphon kind of gets rid of the binary plant altogether. And in that application would eliminate or replace ORCs.
And I will say that also this is a project-specific answer because it depends on the range of temperature. So there are some range of temperature that certain organic ranking cycles can work and also and have good performance. And also water can work in some conventional geothermal system. But there are, as Jordan mentioned, many other characteristics, like, for example, environmental issues. So, for example, in our demo project at COSO, we could inject water and supercritical CO2 in the well because it's inert, so there is no risk of pollution of groundwater, for example. But then, if we have designs that combine a working fluid on board with a working fluid in surface, so we can also optimize the heat transfer and power production. So I think that it depends on the project, the potential of the system and the reservoir. So we can optimize the design for each specific project.
I want to agree wholeheartedly with Alvaro and just reiterate. I think the end solution is going to be a combination of ORCs, sCO2, thermal siphons, water, a typical ranking. I don't think there's going to be one that's going to clearly dominate all of them.
Yeah, great. So one of the next couple questions I'll kind of group together. So disadvantages of CO2, what are those? You know, right now it's expensive to buy. Ironically, we mine it. Do you have comments on that? And then someone else says, cost. Please inquire of the panel. We are trying to drive down cost in geothermal. So what do you guys think about that? And maybe Alberto, you could take this one.
Yeah, so let's say about cost, of course, the high pressure, the higher pressures, especially for subcritical application where we are really developing our systems, is one of the challenges. In our case, we are moving CO2 to in a district, so to provide energy services. We are already doing that in industrial refrigeration, so there is this pressure concern, but we have also in our case a low temperature, high pressure application, which means that, for example, we can move CO2 at more than 600 psi with reinforced thermoplastic pipes. So, for example, reinforced thermoplastic pipes in low temperature applications are really helping to reduce the costs related to CO2. Then, of course, when we compare with water, the downscale in volume, it's really helping in that direction. I don't know if the others want to add on my answer, especially for high temperature application where we do not have really a big experience.
I would like to add that when we analyze cost, so we are analyzing basically the LCOE of the project, and LCOE is probably one of the most important decision maker factor for different project alternatives. However, going further, not always the higher LCOE alternative will give you the best sustainable production in terms of, for example, exergetic economic analysis. So an exergetic economic analysis is based on the second law of thermodynamics, and it says that the entropy always produces heat losses, and these heat losses can be as a function of mass or also as a function of energy losses. So it means that a project that can be very economical at the beginning, probably in the future cannot be sustainable because there are some waste of water, carbon emissions, greenhouse gases productions, carbon footprint in the project, or excessive water usage. So I think that cost is very important, performance is very important, but also sustainable analysis is very important.
Great. So another question from the audience. So apart from CO2, are there any other engineered working fluids that are of interest for low enthalpy geothermal? And what about engineered solutions and fluid combinations?
So I think one of the next exciting things that we're hoping to research more is using mixtures of CO2. I've heard some people call it CO2 doping, but basically, like I mentioned earlier, for example, it's not the only thing, but where the critical point is kind of really drives your efficiency and your cooler cost and all that. And doping CO2 with other mixtures helps you kind of adjust that. And so we definitely think that mixing mixtures with CO2 or other refrigerants might be a really cool and elegant solution to some of the problems with CO2. There's still a lot of research that needs to be done on how those mixtures combine and what happens with dropout with one versus the other and things like that. But I think it's an exciting path forward that you could really start to get to the point where you're optimizing for a specific location just by the percentage of 2 or 3 different fluids.
Mm-hmm. Yeah, I think we're finding in our research that we typically get a better thermal cycle efficiency out of organic fluids, particularly hydrocarbon-based. The problem with that is that they have much higher global warming potential values than, in comparison with CO2. And they also typically have a higher flammability, obviously, as well. So we're hoping to find the medium situation where we can have good thermal efficiency, but lower global warming potential and lower flammability as well. So the doping, we're hoping that we can find the right mixture that will get a good combination of those properties.
Yes, thank you, Michael, for raising this global warming potential concern. What I can say is that what we see in the HVAC and refrigeration industry is that there is the tendency to accept lower performances in favor of environment-friendly fluids. That's why CO2 is being adopted in many applications, not only in power cycles. The other fluids, natural refrigerants that it's worth mentioning, it's ammonia and propane. Those 2 fluids are flammable fluids and more toxic than CO2. And this is also explained why the whole world is going really in the direction of closed circuits with working fluids, with CO2 as a CO2, or as we said before, doped CO2 as a working fluid.
In GreenFire Energy, we are open to use different working fluid, and actually that's one of the activities that we always do. So we test different working fluid performance in our projects, and yeah, we are also contributing to scientific research. As we already mentioned, we have developed since 2014 different research, including the demonstration project at COSO and other demonstrations in the world. But we are open to new refrigerants, so we always test the performance of different refrigerants. And the most important thing is always evaluate as we already mentioned, cost, performance, and sustainability. So this is the basis of our designs, and the working fluid is one of these factors that we include in the analysis.
So follow-up question from the audience is, what other fluids could be mixed with CO2? Could you give an example?
So I think we've looked at both refrigerants and hydrocarbons. I think we're trying to get to the point where we can cast a much wider net than we have. We've also even looked at just water mixed with CO2. And although there's lots of physical problems with that, and that is probably a little bit too much of a pipe dream, it's very simple in theory. And so I think we're trying to cast that net and determine what those fluids are, but I think initially it looks like some hydrocarbons or some refrigerants or some combination of the two.
I'd love to see a carbonic acid cycle. That's great. So a follow-up question about the size of the turbo machinery. So this audience member is asking, so we can put the entire power plants in modular movable pallets and move them around with forklifts? If that is true, that is game-changing. So your comments, is that true, and is it game-changing?
So close to true. Forkliftable, maybe. So the problem is that the turbo machine itself, you probably could get on a pallet. Right now, we're working on reducing the size of the actual generator, which is still kind of large, that you have to hook up to your turbo machine. But you definitely have a skid that could fit on a UDOT on the back of a truck and take from one site to another. It might be a little bit heavy for a single forklift, but getting closer to yes.
Yeah, I think that we can get the turbo generator equipment on a skid. We can get any pumping and heat exchange equipment on a skid. Probably the only part that we would struggle to do that with too easily is the cooling end. So we're mostly looking at dry air cooling. So those coolers are fairly large. But having said that, we could probably get each of the banks or sets of coolers on a truck still. But they would need some further construction work on site to get them set up, other than just putting a skid down onto a base and bolting it in place.
Great. So another question from the audience. Does subsurface characterization and rock mechanics come into play when supercritical CO2 is in play? In other words, does the use of CO2 change our way of site characterization for geothermals? Maybe Alvaro, you have thoughts on this, and you can talk about like modeling for the working fluid.
Sure. Yeah, we mainly simulate closed loop system because we are a closed loop system company, but we also have some patents in semi-open closed loop system, actually using supercritical CO2. And we also can simulate those conditions. But the most important is, as you mentioned in the question, so evaluate the resource and the system. The properties of the rocks are very important. For example, if there are some other process like CO2 capturing and other alternatives, so this is important to evaluate. But then for the closed loop system analysis, yes, our modeling is very important in order to integrate all the ways of energy to optimize the power generation, or in some other system direct use, for example.
Any other thoughts on open loops? There's a question about, is it okay to do an open loop, and what about sequestration combinations for geothermal systems? Any thoughts on that? I know, no, that's not what you guys are doing, but
yeah, I think that in general the downhole heat source design, in other words, the rock formation is critical. It's not a good conductor of heat, so whichever heat source fluid we're using, we obviously need to design that fracture structure to give us the best possible heat capture, irrespective whether it's CO2 or another working fluid. If we're going open loop, in other words, putting the working fluid itself directly into the fracture, then obviously we'd like to have as little permeability as possible, because we don't want to lose an expensive heat transfer fluid into the rock. Most sCO2, I think right now, has been looking at through the thermocycline effect, which is a closed loop in itself. So I don't think that would necessarily be affected too much by the rock formation, but certainly with an open loop, yes.
So what do you all see as the biggest design challenge with regard to the use of supercritical CO2 in geothermal? Biggest design challenge?
Well, I would say that for supercritical CO2, we need to include the special equipment for handling the pressure and temperature conditions, especially if we are working on supercritical conditions. Yeah, but then we need to always consider the advantage that we are we have been talking about this advantage in all this discussion. So there are some issues or some challenges, but as Jordan mentioned in other answers, so it's important to consider all in order to at the end having optimal performance of this working fluid in geothermal system.
Yeah, I think the biggest challenges we are seeing are twofold. One is, I think, as Jordan mentioned earlier, the recompression cost, and the second part is reasonably cost-effective insulated tubing to get down to the depths that we need to make the thermocycline effective.
Jordan, we have a quick question for you. Can you give us a quick answer to this? Who owns the SWRI tech, and is it licensable?
So one of the great things, I'll put a plug in for SWRI right now. All of our projects are either funded by the Department of Energy or commercial clients. So we maintain almost like 99-point-something% of the technology that we've developed usually goes to the companies themselves that we're developing with. So that's generally how our business model runs. We get funded to solve problems, and we're not good at commercialization. So the people that funded that gets the IP and goes and commercializes that.
Great. So we've got about 2 minutes left here. So I want to go around the horn with a final question. So where will we be here in 5 years? Will we have commercial deployment of this? So let's just take everybody just maybe a 30-second answer to this. Alberto?
Yes, from what concerns ExerGo, in 5 years, we will have multiple installations, and I hope that we will be able to couple CO2 networks with geothermal power cycles and shallow geothermal application for heating, but also for cooling applications. So shallow geothermal is really attractive for that as well.
Alvaro?
Yeah, I think that geothermal energy and closed loop system is one of the most sustainable, affordable, resilient, clean, and economic baseload energy in the renewable energy spectrum. So I think that in the nearest future, we will need more from geothermal, and I hope the scientists and also the industry can work together to give to the world this energy transition that is necessary for environmental and also for the economy.
Michael, 5 years from now, where will we be?
Yeah, I think with Sage, 5 years from now, we will have figured out the basic decision points of working fluids and plant design. And we'll have our first plant up and running by then, and we'll be into the phase of learning from that and sharing that with industry. I think that hopefully our peer companies will be doing similarly, and we'll start converging towards a really good working system.
Jordan, what do you think?
So I think at the end of 5 years that we'll be on the back end of the kind of pilot plant / demonstration and on the uphill climb of actually making that commercially viable.
Great. Well, fantastic. So we are at the end of our allotted time for this panel. So I want to pause the discussion that we've been having here today, hopefully to be continued at a later date over beers or something. And I would like to close by thanking each of our 4 panelists for sharing their insights with us this past hour. And thanks also to our audience for spending time with us today. Pivot 2022 is still going strong with more panels and speakers to come through the rest of today. So we look forward to seeing you at the next session.
Thank you.
Good morning, good afternoon, and good evening to a session on the last day of Pivot 2022, when I've certainly learned an awful lot over the last 4 days as a result of listening to the technical and technically economic sessions that we've had so far. This particular one is on a slightly different theme. It's attracting public and private capital to fuel the future of geothermal. And I'm delighted and honoured to have with me Rob Santangelo from Credit Suisse, who will be my interlocutor in this session. And perhaps I just pass to you, Rob, for a minute or two just to introduce yourself.
Well, thank you, Tim. It's a pleasure to be here and join the discussion. Just for everybody's benefit, I'm at Credit Suisse currently running energy and transition investment banking for the firm. I chair our ESG advisory practice within the investment bank. And prior to that, I ran equity capital markets origination for the firm for about 7 or 10 years, working on public and private equity financings and convertible financings, and grew up doing power, energy, and renewables going back about 25 years now. So I've had the benefit of looking at these sectors for a long, long time.
Thank you very much, Rob. And I think those of you who didn't hear me on the previous panel session, I've been in the energy industry for about 40 years, of which roughly 30 has been in oil and gas and a couple in geothermal, and roughly 10 years in energy policy for the European Commission for the Eastern European countries back in the 1990s. And my conversion, if you like, to geothermal is looking at how we can finance geothermal projects, what are the standards that might be needed to do so, and to have Rob from Credit Suisse along is a great pleasure, and I'm sure we will have a lot of things to dialogue about as we go on. I want to start the session by just giving an overview of the global situation regarding finance, just so you all have some idea of the numbers involved, and then perhaps we'll go into some debate. But just to give you an idea, over the last 5 years or so, in the geothermal sector has invested roughly $4 to $5 billion per year. Of that, probably 2/3 in the electricity part and 1/3 in direct heat. And of that, probably 3/4 has been in Asia, barely 10% in Europe and 10% in the Americas. And of the Americas, just Mexico and Chile were the real notable investors. The USA, for example, did not figure even investing $150 million a year. So that's kind of where it is. The other thing I want to do is contrast who is doing the investing around the globe. And so in the Far East, it's a bit of a mixture of pretty well everything: listed banks, state-owned banks. For example, in China, there's a Sinopec joint venture with an Icelandic bank called Sinopec Arctic Green. PetroChina is a big player. There's a Hong Kong listed company called ENN. There's a Turkish company who does a lot of work in Turkey called Gurmat Electric, also privately owned. Then you've got Pertamina, obviously a state-owned company, P&L Gas, state-owned. And then you also got some geothermal specialist companies, for Philippines Geothermal, for example. And the other notable thing is a large number of multilateral organizations, the various banks like EBRD, Asia Development Bank, and the in-country banks as well support them, and private equity. So over there, it seems to be a fair mix of the different funding entities. In Europe, it tends to be private and public sector. The US, it tends to be private companies or public listed companies. The two that are notable within the geothermal sector, which is pure geothermal, would be Calpine, with about a $10 billion market cap, and Ormat, roughly $4 or $5 billion. But they also have very large conglomerates, investment companies like Berkshire Hathaway and Macquarie would also be involved heavily in the California and Nevada space. So that kind of, I hope, gives you a perspective about what's the same and what's different around the world. And with that in mind, picking up on the issue of finance, Rob, in your experience, is there substantial capital for the US international geothermal companies and projects? And who are the big players?
Yeah, so thank you, Tim. I think you raise an interesting point in introductory remarks. Let me just comment. I mean, if you look at global investment in renewables they're probably averaging somewhere around $300 billion a year. And so when you put the lens on geothermal in that context, it's really about 2% on a good day of global renewable spend. And so really the question then becomes, why will it not, and when will it attract a broader share of that investment component? And I think it's quite important that it does. And the reason that it's quite important that it does is because it can provide a very complementary, base load power into the renewable mix, which is increasingly valuable as intermittent renewables take a larger share of the grid. As you look at it, historically, I think the questions that are important is sort of the de-risking of individual projects and opportunity sets. I would say that there's a motivated universe of private equity and infrastructure investors into all renewables, and that would include geothermal. I think geothermal probably has suffered a little bit from being harder, Tim, than wind and solar, which have sort of moved beyond this period of perceived project risk and appear more to be in a deployment mode. Whereas I think geothermal at this stage, at least in North America, has been much more narrowly focused on specific opportunities that create degrees of risk that exceed what is perceived in wind and solar. So, as we sit here today, I don't think we need to name anyone by name, because I think if we did, we would miss 20 interested parties for everyone we named. All of the major infrastructure players, all of the major private equity players, I think would be highly motivated to invest. But there's a caveat, and I'll call that in what has appeared to be a de-risk project. So in the renewable deployment that we'll call pour in capital for sort of a known set of economics, there's a very significant amount of capital. I think in the geothermal space, you don't have the breadth of developers that you do in wind and solar. You have a much more narrow set of immediate opportunities in North America. And therefore, you tend to get the sense of, I haven't done this before. What is the risk profile? What is the return? Most of it has been done, as you correctly point out, by industry players directly. But there is a large pool of capital that would come into projects that are seen as de-risked.
Yeah, this risk issue, I mean, I'm looking around the world and saying, well, what are people doing to try and get these projects going? Because the difference between an oil and gas project is if you invest in an exploration well in private equity, you might expect 5 to 10-fold increase in your money. So you're looking at major upside, and therefore, if you like, when you work out the probability of success being 20% or whatever it is, then you can justify a portfolio of high risk investments like that. But because in essence we're just producing very hot water, then the commodity value is much smaller, and so the rates of return are much smaller, and so the uplift is much smaller. So for someone saying, well, I'll take a punt on a $3 or $5 million well, then it's hard to see the 10-fold multiple in their when they exit in 2 years' time. And so what I've seen around the world is various attempts to put in de-risking right up front at the exploration side. And this isn't my research, but I did read something that NREL did in a couple of years ago, where they looked at the USA back in the 70s and the 80s. And in order to kickstart geothermal power production in California, there were a number of de-risking strategies which would then allow smaller companies to take exploration risk and appraisal risk by supporting with grants and other instruments. And I think the rest of the world has kind of learned from that, because if you look around the world now, there's no end of different mechanisms. I mean, in Europe, Holland and Germany have one. The European Commission itself has just put in a bit of legislation to try and formalize that process. Turkey has EBRD and a thing called Pluto, where they de-risk they ensure the loss of the first well or the first two wells. It kind of seems to be going on all around the world. What do you think in the USA might be done from now to kickstart things?
Well, it's interesting, Tim, you have not seen, I think, the focus on policymakers on geothermal as squarely as you've seen on wind, solar, and most recently on carbon capture with 45Q, as it's related to the recent, proposed agreement in the U.S. Senate. And so I think that you probably do need a greater degree of subsidy around, the de-risking of projects. I think there's also a role for corporates, Tim, in terms of offtake agreements. Once projects are de-risked, you'll significantly compress the cost of capital. There's a number of large corporates that are leading in what I'll call the carbon sequestration, carbon capture game. And I think some of those efforts could appropriately be put towards low carbon generation, specifically geothermal, because of its baseload characteristics.
Yeah. And so, I mean, if you like, the Department of Energy in the States has put down a marker and said they're very interested in geothermal, and they will start to, and they're providing grant funding for R&D projects. Can you see in the political future, in this administration, another one, a major change? Or are we just saying this is what needs to happen? Do you see any chance that it will happen?
I do think you'll have to get past the midterm elections in this country to see what the composition is. I don't think you'll see more legislation before the midterm elections in this country. And then I think it will continue to be a very significant topic in Congress because there's a very strong desire, I think, across the aisle, to drive energy security, energy efficiency in this country, and renewable power. So I think hopefully we'll see some more activity post the midterms.
Okay. I mean, I'm conscious that you're based in the States. I mean, does Credit Suisse have operations more globally where we can discuss your views about what's happening in Europe or the Far East, or should we mainly focus on?
We can discuss globally that Credit Suisse does have a platform globally. We probably have partners of mine who are more expert in Asia or Europe at the micro level, but I'm certainly familiar at a macro level. Well,
just to that point, then, do you see that the chances of getting projects accelerated are better in the Far East or Europe than they are in the States?
There's certainly a higher level of activity in the Far East, and specifically around Indonesia and other places where we expect to see quite a bit of continued activity. And I think you do see quite a bit of activity in the US. It's just small by the scale of the power complex in the US. So if you're looking at California and Nevada right now, and Utah, there's active processes ongoing in each of those states. I think many of those will be captured by incumbents and to a large degree be self-financed, given the scale of the opportunity versus the scale of the companies.
Yeah, but whether it's the Far East or the USA or Europe, I mean, I did a back of the envelope calculation, and it seems like just about 10 watts per person is what the geothermal industry is contributing to, for example, the US public. It's as utterly trivial, and so it's about saying yes, sure, the Far East is ahead in terms of current investment, but it's still only $3 to $4 billion a year. How do we make that $30 to $40 billion a year, both in the Far East and indeed in Europe and the US? I mean, it's that kind of step change that's going to make the difference in terms of putting geothermal into a useful position for decarbonisation and the transition.
Yeah, I think that's going to have to happen through, some form of combination of public and private incentive. You're going to need to see, there's been a tremendous amount of corporate PPAs given to wind and solar, and it has supported the development of those projects. I think the same approach to geothermal. I think what has been more difficult in geothermal is the breadth of projects being presented as just needing an offtake or just needing capital. Each of them have involved some degree of more associated project risk, and so it's that pre-construction capital and the pre-offtake that I think is where there's the greatest need.
If I look at the oil and gas industry and its extremely efficient capital markets globally, I think it's to an extent underpinned by an understanding of water reserve and water resources. That, for example, the SEC will ask you to report your proved reserves, and other parts of the other jurisdictions will say the proved plus probable reserves and resources. And there are strict rules for evaluating these things, and there's a whole industry of consultants and experts, third parties, who do this for projects that come to IPO or require rights issues or class 1 transactions. And my kind of observation is I don't see that within the geothermal space. And therefore there isn't a way, if you like, of Credit Suisse talking in a common language with someone with whom they want to syndicate a loan, or with maybe, you know, multilateral organization. There isn't that common language of a resources a standard, a reserve standard that is sort of prescribed by law or by stock exchange regulations. Does that kind of drive with you that at the moment we can't all talk the same language?
You know, I think it's certainly, I think it's a combination of you know, you can have technical reports on geothermal that could give you some comfort, but it lacks, I think, two things. One is the standardization and familiarity with, I've seen 100 of these, and therefore on the 101st, I have a reasonable expectation of how it might be high or low and what might cause that. I think it's still an area where many people would be looking at these types of technical assessments for the first, second, or third time, and therefore far less confident in what the outcome would be. And secondly, if you look at oil and gas and the development of drilling generally, even maybe prior to the last few years, when the cost of capital in oil and gas have gone up for ESG and other reasons, nonetheless, the cost of capital of a subsurface activity has significantly exceeded the cost of capital of sort of above ground activity, right? So you could compare, for instance, the cost of capital of the transportation business of pipelines to the development of reserves underground, and you'll typically have found quite a different cost of capital. And I think the same is true with the renewable business. I think right now, you know, renewable wind, renewable solar are above ground, relatively well-known risks, and are seen as really just a bit of cost of capital into a relatively finite span of productive output and cost. And I think the geothermal suffers from a greater degree of uncertainty as to whether the project will be viable in the first place. And therefore, one might think about, Tim, whether there's a public-private partnership. You know, certainly you've seen this in the fusion space, where you've seen significant private investment into maybe de-risking projects, taking sort of a venture type return to de-risk projects, get them to a stage of development where then you would have infrastructure and corporates that would clearly support baseload renewable power.
Yeah, I mean, I'm almost tempted to say, well, are there really any differences in the risks which an investor would face for a geothermal project than an oil and gas project, in terms of the range of uncertainty and its outcomes and the things that can go wrong, both in the understanding of the subsurface, the construction risks and the delivery risks? And I suppose that kind of pushes you to say, well, a neutral investor will be demanding a similar equity rate of return to that which they would require for an oil and gas project.
Yeah, it is interesting to, to consider whether, some of the folks that are developing would skew partnerships towards some of the major or large independents whose skill set may help them assess the subsurface risks, and who also are pressing, their own transition strategies. In Europe, much of that transition has been in the form of wind and solar of the majors. And I think that's probably seen as more quickly scalable than geothermal. But I think geothermal ties into the core competencies of many of these companies very, very well.
Yeah. One thing that the European Union has done, which isn't there yet in the States, is introduced these carbon pricing mechanisms and other ways of trying to level the playing field between fossil fuel energy sources and zero carbon energy sources. And one indeed notably is electricity generation. So the generation of electricity is part of that carbon trading scheme. And in your perspective, has that made a difference to the incentivizing of investment in geothermal energy across the world? And does therefore the US lag behind in terms of those incentives, or do you think it's pretty marginal in its impact?
I think that I think if you look at Europe, where you have the carbon trading mechanism, it's certainly driven selection of renewable versus fossil energy, although it hasn't had the effect of driving it to geothermal for the most part versus wind and solar. I think that carbon pricing mechanisms are sort of an economically sound way to let the market sort out different technologies and different solutions to low carbon electricity, Tim. And I think for that reason, we should encourage them. I think there's probably an additional step that at this form of its maturity would help geothermal. Meaning if you look at wind and solar early on, other technologies early on, if you look at the carbon capture business today or carbon to value chains today, they're benefiting from very narrow and specific, policy support so that they can quickly move down the cost curve, right? And I think that's in geothermal, an important part of it is moving down, not just the cost curve, but the de-risking curve.
Yeah, absolutely. In terms of the capitalization of the companies that might come to an investing source such as yourselves, if it's not an oil company, instead it's a geothermal company, then historically they've been relatively undercapitalized, and therefore I would imagine rather more difficult to finance. Maybe they're more like a startup or with a good idea and some people and not very much money. Now, how would you go about helping such an entity to get on their way? And
well, I think it's a really interesting question, and probably one on the minds of a lot of our attendees. I think that if you think about where there's both motivation and expertise, I would say there's a large component of private equity firms that have historically invested in oil and gas that have largely stopped, but that institutionally retain a skill set of assessing subsurface risks. And many of those also have large infrastructure and other pockets of money that accept a lower risk of return for construction capital on de-risk projects. And so I can think of a dozen names off the top of my head probably that would be probably well suited, because with a relatively small amount of capital they could participate in sort of a de-risking of a project, and then would have pools of capital to deploy into construction of projects.
Yeah, there's a couple of questions which I might come to in a minute in the chat box, but this I just never get my head around this, which is the risk is the risk, and so even if you've got a different fund that maybe doesn't demand such high rates of return, ultimately, if this is going to scale, then you've got to match risks with return on equity some way or other. The two have to be at an efficient frontier. Otherwise, as a pension fund or a private equity firm, you'll be investing elsewhere in real estate or something else like that. So I don't see how we can get away from the fact this is intrinsically a risky thing to do, and is intrinsically doesn't produce a lot of value compared with oil and gas. Now, how do you get around that?
Well, I think Tim, you remember that the capitalization of the cash flows will be different, though, right? So, for instance, a producing project in geothermal will be capitalized at relatively high multiples of cash flow, and an oil and gas project with a set number of cash flows is going to be characterized by a relatively low multiple. But you're absolutely right. I mean, I think that investors are going to demand higher degrees of return for this type of a project than for, a wind or solar development for sure. But I think the biggest thing you may have is that many people will not feel capable of assessing the risk. So it's not just what is the return, it's can I assess the risk in the return? And I think for that reason, and I think that if you can assess the risk and return, but then can't participate in the project aggressively once it's de-risked, you're at a disadvantage versus the type of a fund that can both assess the risk, but then has the deep pockets to build, these might be people who've built pipelines, gathering systems, LNG facilities, power plants, lots of infrastructure, roadways, with deep pockets to deploy into scalable projects. And so I think you'd see the greatest degree of attraction where a reasonable amount of exploratory work can de-risk a relatively large future development, if that makes sense. I mean, the big potential resource that once it's delineated, and that's what you see also in the oil and gas space, Tim.
Do you made me realize something, that the essence of why oil and gas has been so successful is that there are so many exit points recognized and with all the support structures necessary to do those exits. So for example, just take an exploration project. You might use a company which is undercapitalized to establish that there is something there, maybe even drill a first well and make a discovery. And then they'll then demand a farm-in in order to progress the rest of the project, maybe have a carry of 10 or 15% through until first production. Now, it's a bit early days yet, but now I think about it, then that might be the way in which you divide these pots of money up, not just within an institution, but saying across institutions. These are the hedge funds or the people who want an 18-month in and out and a 5-time multiple on their money. They will exit across to, as you say, someone who builds pipelines and LNG facilities for a living, and therefore can take that at a lower rate of return and make money from it as well.
Yeah. No, I think Tim, that's right. I mean, I think that I see two different points of risk. Most of the money will deploy at sort of moderate risk, probably higher than a traditional pipeline still in terms of what the facility will produce and the cost to build. And part of that, again, we're seeing in the carbon space are corporates that are willing to help drive activity at some incremental cost to what they could maybe, buy it for. So Stripe has got the Frontier Fund dedicated exclusively to picking promising technologies and helping them drive down the cost curve by buying credits effectively above where they're trading now, with the hope that they can help drive them down to much more economically viable numbers.
Yeah.
Microsoft has done a fair bit of that as well. And so there are companies that will look at this and, are looking for a return, but are also looking to help drive broad decarbonization as part of their strategies.
Yeah. So what we're saying is that at least initially, where the operating company rather than their shareholders are doing the voting, then it's possible to compromise a bit on rates of return that from this industry rather than the one they're traditionally involved in.
Well, I think that they see in that a variety of benefits in human capital, in meeting their own decarbonization goals. Many of these companies believe that it'll be hard for them to meet their decarbonization goals unless these technologies are advanced and come down the cost curve.
Yeah, I get that, and I think there's two phases of this. One is the phase where people swallow and say, okay, all right, I'm accepting a low rate of return because it means that I've fulfilled my ESG objectives, and I'm hopefully contributing to a reduction in overall cost per kilowatt hour generated. I get that, and then there has to be a phase when the thing matures and we get back to rates of return that are commensurate with the risk.
Correct. And the risk is perceived to be far different because the projects have been built, construction costs have been delivered on or missed by certain amounts, and people can then calibrate, from their past experience and from the experience of the industry, what the likely variances are. Yeah. I mean, I think one of the things that is an important driver in the early stage of an industry is the perceived variance of results. Yeah. And those will naturally be set at wider in the beginning than as the industry matures.
Yeah, I mean, there's a premium for ignorance, and that's what's happening here, which is people don't know yet, and therefore they have to be more cautious in what they think, what the level of risk they think they're. We got a couple of questions, one of which I thought we touched upon, but maybe we didn't do so in sufficient detail. But I'll pick it up. It's talking about using insurance policies to mitigate the early exploration risk. So that's the first well. Or the first two wells. I think we did touch on it briefly, but just to kick off that, then, for example, the European Commission has just set up, or a new piece of legislation to formalize its process across all of the member countries. It was before trailblazed by Holland and Germany, and France as well has done a lot of this kind of stuff. But now there is a policy in place where a company can go to the European Commission, pay a premium. I think in Holland it was 7%, and on the basis of that, they get most of the money back if a well doesn't achieve its proved, as in P90, capabilities, and the various obligations arise. So just to pick up on that point, which is easy to answer, and around the world, these policies are commonplace. They've all got different hairs and wrinkles. The one in Turkey is called Pluto, which EBRD manages. And in the Far East, you get a mixture of public and private money. In the States, as I said, as far as I know, there hasn't been anything for 50 years. I'm just picking up on that, Rob. Have you heard anything in New York saying, well, let's set up some kind of an insurance policy to mitigate risk on early stage?
You know, we've not seen that as a central part of the climate discussions in Washington, and I think that's you know, and obviously, to my degree, that we're familiar with the sort of most recent agreement between Schumer and Manchin, it does not appear to be part of you know, of that proposed legislation. So in the immediate term, it feels to me like there's an opportunity that's being missed. That, you know, again, and I think as I started my comments with Tim, I think geothermal is a particularly interesting renewable technology because of its ability to provide a baseload power, which is extremely complementary to the grid and increases the value of, you know, intermittent sources of power, right? So I think policymakers should spend more time thinking about accelerating the growth of geothermal, for sure.
Yeah, that's interesting, because my observation over the last 5 years or so is that although we all know, everybody must know that a 24/7 baseload supply is worth a heck of a lot more than an intermittent supply that relies on the wind or the sun, utility companies in the States are not paying for that. There are exceptions, but generally speaking, they say, well, okay, it's a tiny supply in, so far as we're concerned, we'll just treat it as a supply. So that will change, I think, and earlier.
Tim, I agree with that. I think in the early part of renewables, if there's a big grid and a relatively small component of renewables in the grid, the cost of intermittency in sort of a real basis is much, much lower. As renewables or intermittent resources become larger as a percent of the grid, and as a grid has less sort of interconnects with other large grids that it can borrow from when it right, then obviously the cost of intermittency goes up, and the value of base load goes up.
Yeah.
And so, you know, I think the U.S. has made substantial progress in renewables, but trails Europe. And I think that as we make more progress, and I see, you know, really significant acceleration of capital deployment in this country, and it's very heartening. I think it will naturally bring people to identifying other base load, you know, sources that are renewable
and reward them. Yeah. The one thing, just before we finish on insurance policies, I mean, there's one way you can do it, which is quite common around the world, which is you rely on policy and a government to do it. But actually, it's also a straightforward business opportunity. So if you're well capitalized, and like Munich Re tried to do this, I think probably 20, 30 years ago, but they couldn't get traction. But there's no reason why an insurance company cannot acquire the skill set required to evaluate geothermal projects and say, there's a business here. There's one small company called Parhelion. I think it's a British company which teamed up with Geothermex, which is a Californian operator. They're looking to do this kind of stuff in Africa. So I just don't want to leave people with the idea that it has to be a government-funded or a multilateral-funded insurance policy. There's money to be made, so any insurance company can have a think about it.
And it's also a very interesting opportunity, Tim, for, again, traditional energy companies to partner with an insurance company. You know, people who have deep subsurface expertise and who do that with sizable capital all the time may not have an insurance license, may not be an insurer, but would bring to them a capability that I think they'll view as very attractive and very valuable.
Okay, this I'll raise this. That was almost put in the chat. This issue of more than one stream of revenue, and I'll read the thing to you. So, what's the ROI of a geothermal project versus wind or solar? We've covered that. Can we add value to a geothermal project through a holistic cascading use approach? For example, co-production with gas, minerals, or hydrogen. So more than one stream of revenue. What's your reaction to that?
Co-production with gas, minerals, or what?
Well, I mean, they're just saying for gas, minerals, or hydrogen. The minerals one is a lithium discussion that's been taking place around the world, but especially in California, where Berkshire Hathaway and are looking to co-produce lithium from their hot water streams. But those are specific examples where you've already got the geothermal project there. So actually, it's an add-on rather than a kind of new concept. But as a concept to go to a bank with, hey, we're going to produce heat for electricity or direct reuse, and we're going to produce lithium. How do you think that Credit Suisse would react to that?
I think that it obviously creates more upside, but it's going to still leave the project in the, with better economics, but with the same, the same challenge of finding a source, which exists, that feel like they can understand those risks and assess them. You're still going to have, projects that is certainly an improvement to the project because it brings on the potential for meaningful additional revenue, to drive returns higher, et cetera, and to reduce effectively the cost of the geothermal power or heat. So it's certainly a positive, but that in and of itself, I don't think would relieve the burden of, finding folks that feel that they can assess it at the early stage, and then feel that they understand the variance of costs and recoveries of a working project. So I think clearly enhancing project economics is good, but not a silver bullet. Yeah,
I mean, I actually posed this question to Goldman Sachs about this time last year, and the reaction was, well, that's a whole other stream we've got to try and understand and get our head around before we can think about investing in either of them. So rather than regarding it as a major opportunity to have, mitigating stream, I said, okay, well, now we've got to understand lithium and all the risks associated with that before we, as well as understanding geothermal and the risks with that. So I thought it's interesting that you've come up, Rob, with a pretty similar answer to which I heard a year ago. And I kind of with that, now we've got to say, who's going to be the expert in lithium production and resource assessment and all those other issues. Okay, well, we're unfortunately getting on for short for time, but I want to ask you a rather more light-hearted question, but one we did touch upon, which is Credit Suisse is in the business. You're looking to both finance and potentially help IPO companies doing this kind of stuff. So tell me, what are you looking for? Both management team and everything else. Tell me, give the audience a bit of a taste for the recipe they need to come to you with in order to at least get a hearing from you.
Sure. And as you know, Tim, our job is to help companies raise capital almost exclusively from third parties, private and public. And so we have a very good sense of what, folks look for. And I think it usually starts with management and experience. Have you done this before? And that's kind of what at an early stage of an industry can slow it down because you have fewer management teams who've come and said, I've done this once, twice, third, and I'll do it again. And then obviously they look at project economics and they look for variance of project economics and an understanding and comfort with the key risks, kind of the known unknowns, right? And then also the less familiar are they with the project, the unknown unknowns, what don't they know is unknown because they haven't done this enough. But I think it starts with, proven management team and then goes into project economics, project risks above ground, below ground, et cetera.
What about jurisdiction?
Certainly is a big factor. I mean, you'll see that investment in the jurisdiction is going to play a part both in terms of the incentives that a project gets, so what the returns of the project are, and then also the discount rate, meaning investments in OECD countries, US, EMEA, will get a substantially lower discount rate than non-OECD.
Yeah. Rob, we've run out of time, and thank you very much for a very, very rewarding and interesting discussion and debate. And I wish the audience well, and thank you very much for your attendance.
Thank you, Tim.
Yeah.